All right. Test 2 is in the middle of being graded. Multiple choice have been done. I got to get it, add it up, record it, all that fun jazz. Best guess, between 2 and 3, most likely. What we have here is, for test 3 material, it's all going to be about optics, light, stuff like that. Just so I write it down, problem set 8 is due on Monday. No, I take that back. It's due Friday. Problem set 9 is due on, not Saturday. Oh, I wish that was true. Monday again. And then on Tuesday, what's the schedule like? So those are when the problem sets are due. And yeah, because Tuesday is the test. And oh God, hold on. Let's all ignore that for the last 2 minutes. Problem set 7, problem set 8. This is due Friday. This is due Monday. Test 3 is Tuesday. And this is why I'm so confused. There is no problem set 9. This is all because of the July 3rd holiday that they just decided to install. And excuse me. So test 3 material is all going to be about light. And what I've done on Blackboard already, posted the problem sets, posted the sample test 3 material, I've posted the final sample material. It's all out there right now. So you can start getting ready for the final, and even now. With light, what we're going to do first is talk about, this test is interesting. It's a little bit different. It's very visual. It's something where it's not required that you bring a ruler, but it's heavily recommended. I won't bring extra rulers because a lot of this, well, not because, if I brought 50 rulers, that would just be too much on my part. But bring a ruler, it helps. If you really need a ruler and you don't have one, you can just take a sheet of paper, fold it in half, and you can kind of treat it like a ruler. This is my favorite ruler. I've had it for a couple of years. I really like it. I've tried a lot, and I like it because it's clear and it's wide. And it's my ruler. I like it. I'm a fan. The first thing that we do is understand light is lazy, or as I like to say, efficient. It does not do anything that it doesn't have to. If it has to do it, it'll do it. If it doesn't have to do it, it won't. Light's kind of tricky. Is it a particle? Is it a wave? Answer, yes. Is it a particle? Yeah. Is it a wave? Yeah, but you just told me it was a particle. It's both. They call it wave-particle duality, in a way. With light, the first thing that we understand is the law of reflection. and that if you have a mirrored surface, oh, and the other thing about that's also on Blackboard is there's a PDF called Optics Notes, which is a lot of the graphics that I draw, but I draw it in far more precision. So all the reflection, refraction, thin lenses, single double slit, thin film stuff, all of that is on Blackboard on its own little thing. So law of reflection, this dotted line here is the normal line. And the normal line is perpendicular to the surface of the mirror. The law of reflection states that if you have a ray of light hitting a flat mirror, and this is a flat mirror, that angle there is the angle of incidence. And then what happens is, this is not to scale or exact. Actually, I can kind of cheat right here. And this is the reflected light. This is the incident light. And then that is the angle of reflection. So the angle of incidence and the angle of reflection, in the law of reflection, theta I is equal to theta R. And so that's pretty simple. But there is, as an example, one of the questions that they ask about in lab, sometimes it's a quiz question, sometimes it's an exam question. I think it is in the worksheet. Or is thin lenses the second lab report, or is...
It's RC circuit.
The second lab is the RC circuit lab? Okay, all right, that's fine. So there may be a question about this that's coming up, is that you have a mirror and it is 6 meters tall, or not 6 meters, it's as tall as you are. So that's the ground, that's the mirror surface, and then my poorly constructed stick figure man is like this. And the question is, how high of a mirror do you need in order to see yourself? Like, what's the smallest mirror that you can have when placed in front of yourself that you will actually see your entire body? Now, what I'm going to do is, when you think of this body, I'm going to think of it as like a plane, because if we were doing a really more thorough examination of the rays of light, it would get complex fast. And so there are 3 points that I'm interested in: the head, the waist, and the feet. And let's just say that the top of the head is where everything is seen. For rays of light that come in at a perfect 90-degree angle, the ray reflects back at that angle. Because what's the angle of a ray heading straight at a mirror? 90 degrees. Well, what's the ray going to bounce at? 90 degrees. So there is, I mean, it reflects, but it reflects in and out at the same angle. Now when you look in a mirror, you see your whole body. And the rays that you see representing your waist are rays that bounce. Let's see. They bounce kinda like that. So that the light that you see representing your waist is actually light from your waist that reflects, and it reflects exactly like the law of reflection says, and it does it like that. The last ray, the ray from your feet, does like this, and I'll draw it in red just to be different. Show that ray. The ray from your feet do this. So once again, theta I, or theta R, that's a horrible theta R, and theta I are equal again. And what you see is, if you have a full-length mirror, which half of the mirror isn't being used? It's the lower half. This part of the mirror, I could destroy this part of the mirror here, and it would work just as fine. As long as that piece of the mirror and above is there, you don't need it. And so if you are 6 feet tall, you need a 3-foot mirror. And it's a shame that I wrote that right there where I really shouldn't have. But what we see is, if you took these light rays and you simply traced where the ray would have gone had it passed through the mirror, and here you trace back away from the ray that reflects to your eyes. So in all three cases, you're looking backwards at the light, where it appears to be that these rays, now remember, these rays come from 3 different sources. It appears that at this particular location, I mean, when you look at a mirror, what do you see? You see a reflection of yourself. If you're 3 feet in front of the mirror, it appears that the virtual image is behind the mirror. This is what we would call the object, and that the virtual image is behind the mirror. We can also say it's virtual means that light doesn't focus or pass through. It's simply it's simply a mathematical construct, but it allows us to sit there and visualize what's going on in terms of the object. When you work on this lab, one of the things that they're going to have you do is you're going to have a mirror. This is from above. And what they're going to do is, this is the mirror. They're going to have you put, and let me put the mirror line so we can all see what's the real side. So this is the real side, or the object side. So the mirror's like this. This is behind the mirror, that's in front of the mirror. And what you're going to do is you're going to take 2 pins and you're going to place them so that one is behind the other in a particular direction. And what you're going to do is you're going to look at the light that comes from both of those pins and heads in the same direction. And according to the law of reflection, you're gonna look back at it so this is a pin and that's a pin and this is the incident ray. And what you're going to do is you're going to look that's my eyeball sign. So you're going to look from that particular perspective, and it's not something that on a sheet of paper, really how it kind of looks is if I hold it like this. Now I'm over here physically and I kind of look down right where that eye should be. And this is a sheet of paper in lab. This is a mirror. They're little pieces of, it's resting on a big cork board. And what you do is you see in fact, this has to be solid because that's the light actually doing it. So you're going to see that reflected ray. And what you're going to do is you're going to place more pins and the pins line up with the pins in the mirror. So you're going to look and place 2 pins. And what those 2 pins are is it forms a line with 2 pins you look at these 2 pins, which are reflections of those 2 pins. And those line up. So it's a lot like if you're looking at it from head on, what you should see are, if this is the mirror, you should see 2 pins that are green. These are the reflected images of these. and there should be right on top of it. Oh God, this is a horrible picture. When you look into the mirror, you're gonna see 4 pins. 2 that you placed that are red and the 2 that were originally green, and they all 4 should line up. There's only one axis on which this is gonna happen. So you're gonna sit there and line all that up. And this is practice for what we're about to do now. If you have now in this particular case, what we're going to do is we're going to have the mirror. This is the mirror side, and we're going to have a pin here. Now I know what's happening. There should be a virtual pin. Oh wow, that's a miracle that lined up. There's a virtual pin right there. And what you're going to do is you're going to look in the mirror and you're going to place 2 pins you're going to place these 2 pins and they line up with this, so that when you draw the line, you get this. This is one of the reasons why I love 214 Test 3 material, because then I just get to draw pictures and stuff. And what this is all it is just a reflection from the pin light here, and then it reflects back to your eye. So notice how it reflects. And what they're going to have you do again is you're going to line up, you're going to look in a particular direction again and place 2 more pins. So you're going to change your perspective, and you're going to look at the 2 pins and they will line up again with the virtual image over here. And so to trace the rays again, you get that. And so that is the reflected light from that. And in both of these cases, that incident and reflected angles are the same, and these angles in red are the same. Now, those obviously are different angles. But what we see here is that from 2 different perspectives, when you place the pins in the board, they are reflected from the object, but the lines trace back, and this is our virtual image. And so they're going to do this, you're going to do this with a few of the pins. The grand experiment that they have you do is, I'm not going to draw all the rays, but I'll outline what goes on, is you have a mirror and they give you a triangle. And so what they do is they give you the triangle And what you do is you put 3 pins here. And what should happen is you will do what you did here. You'll do 2 for each of these points. So you'll have 6 pairs of pins. And what you will discover is that the pins will line up and form a virtual triangle. Now granted, I mean, you guys are just taking this for the first time, so the image that you create over here is not gonna look, it's not gonna look awesome unless you're very OCD-ish about it. But what happens is, you'll do like 2 pins in green. I'm sorry, 2 sets in blue. Actually, I am going to draw this all out. So you've got 4 pins and they all line up with this one. And then you're going to look at this guy and go from 2 other directions again. Pin, pin, line, dotted line. And then it doesn't really matter. What I tend to do is I tend to go in wildly different directions so I can get a more accurate answer. And you do 2 pins like this, and then it lines up with that. And then we'll do really bizarre things for this one. 2 pins here. Now granted, it's coincidence that the red crossed with that. And then 2 pins here. And now it's really starting to get complex. But what I'm doing is the lines in blue line up with this pin. The lines in green line up with this one. The lines in red line up with this one, and you notice that there are 1, 2, 3, 4, 5, 6 pairs of pins. And so you end up with this, and ideally you should end up with a triangle here. Now it's something to say it, and I get this every year. You look at this and go, I have no idea what it means. But when you go in the lab, what you do is, I'm going to pick this up, or actually I'll pick this one up, is if this is the board, you literally just look down, you put your eyes on the level of the cork board, you see the mirror, and then you see an image of the pins in the background. Don't pay any attention to what's going above the mirror, but look at the mirror itself, and you literally just have to sit there and go, put the pin back, and bam, right there. And you got to do it for all the time. So you can't look down on it. We want you to look parallel to the surface of the cork board and have you work it out like that. That's a much better way. And all of this deals with reflection. Because when you look at all of these and you were to draw it out, at each of these, I'm not going to do that because that's just way too long. It'll be like this, that the rays all line up. So that is reflection. Then there is, and this is a lot more involved, there is refraction. In refraction, light in a vacuum travels at 3 times 10 to the 8th meters per second. In any other medium, it travels less than 3 times 10 to the 8th meters per second. So the speed of light is 3 times 10 to the 8th meters per second. In any other medium, it travels slower than that, with one small exception. Now granted, the speed of light, c is speed of light in vacuum. V is whatever speed of light. Side note, great regret that I could never teach in this class because we just don't have the time. I want to teach like special relativity, like you're a particle traveling to another planet at 2/3 the speed of light, time shifting, all that fun stuff. Speed of light in the medium we just call c. There is one example. It's like speed of light in air is equal to c. Now granted, it is slightly less than c. It's like 2.999, but effectively, as far as, I mean, just as I say in Physics 2.13 that g is 10, in 2.14, speed of air in light is 3 times 10 to the 8th. We're going to just use c. The ratio of c over v, the speed of light in a vacuum divided by the speed of light in that medium, is equal to n. And n is the index of refraction. So the index of refraction n is c over v. So common n's, one of the most common is water. So n of water is 1.33. It's a ratio, no units. So c is meters per second, v is meters per second. You divide one by the other and you get nothing. N of glass varies, but typically it's 1.5. It all depends on the material. Water is 1.33. Glass is pretty much whatever I say it is. Or I give it to you, or I'm looking for it. It's one of those things. But typically it's the typical n's that we deal with are greater than 1 and less than 2. We're not going to be dealing with materials that slow the speed of light to 0.5 c. It's not going to happen. So if we had question, what is velocity of light in water? We know that N is C over V. So V is C over N, which means it's 3 times 10 to the 8th divided by 1.33. And that gives us 2.26. And that's the velocity of light in water. So it slows down. If light goes into any material, it slows down. Some scientists have been able to get it down to like a meter per second. It depends on the material. And really what's happening is that the light comes into the material absorbs that light, and then it re-emits it in a continuing fashion. And that absorption emission time is effectively slowing it down. Light going through a vacuum doesn't have to be absorbed by anything, so it just moves. Light changes its velocity from medium to medium but its frequency never changes. The frequency of light never changes. Never? Never. So if you have, I'm going to use a nonsensical value. Well, let's figure this out. Why is it this way? Quantum mechanics says so. And it's all because of frequency. What they found out is that frequency is directly proportional to the energy of the particle. Energy is conserved. So a certain frequency photon has a certain has a certain amount of energy, an amount of energy that doesn't change. So its frequency must be constant. Typical wavelengths of light. Wavelength of light is the distance from one peak of the light to another peak of the light. It's a lot like when we were working in with waves in 213. And in light, and this is, well, what's changing? Light is an oscillating mix of E fields and B fields. And there's a whole chapter on this in the book, and the book that we don't really use, and a chapter that a lot of professors don't even touch. But light, if I can draw it, this is the E field, which is, oh, hold on, let's see. E, B, all right. And B field is like this. What happens is in blue, the E field wave looks like this, and on the vertical axis it looks like this. I draw a better picture. Look in that. But these E field lines and B field lines are, and I mixed it up, are alternating. And there are all these wonderful pictures, but the bottom line is, light is a mixture of E fields and B fields, and their values are alternating. And if this is the E max, the length between consecutive E maxes is the wavelength itself, or consecutive B field maxes, or B field mins, it doesn't really matter. But there is a distance associated with it, there's a velocity associated with it, there's a frequency associated with it, and the velocity is lambda f. That the velocity of light is the wavelength times its frequency. Wavelength is in meters, frequency is in inverse seconds. Multiply the two, what do you get? Meters per second. So in the typical lambda, I'll use 600 nanometers. Nanometers is the usual length used for light, or light's wavelength. Nanometers. And 1 nanometer is equal to 1 times 10 to the negative 9 meters. The other length used is angstrom. And angstrom is an A with a circle on top. And 1 angstrom is equal to 1/10 of a nanometer, which is 1 times 10 to the negative 10 meters. And so when you're playing around with optics, you see a lot of nanometer units, you see a lot of angstrom units. And so if I ask for the typical answers when I think about light, I tend to use nanometers. When we're asking the question, what is the frequency of 600 nanometer light in a vacuum, you take that equation, and C divided by lambda is equal to F. If you take a frequency of light in a vacuum, multiply it by its wavelength, you can get the speed of light from it. One of the things that you could do, I don't recommend, you can look it on YouTube and see the demo without having to risk setting your apartment on fire, is that you can get that value C by using your microwave. There's a certain experiment that you put something in it and there's a pattern that forms in this material, and then you can study the burn marks and get a wavelength, and you look at the frequency of the microwave, and then you can get the speed of light from it. This gives you 3 times 10 to the 8th divided by 600 times 10 to the negative 9. And that will give you, yeah. Oops, what did I do? Oh, 3, 8, divided by 600, 9. And that gives me 5 times 10 to the 14 hertz. So it is, I mean, it's a very high frequency. It's light. This light passes into water. I want to know its new frequency, its new velocity, its new wavelength, all these things. The first thing that I would say is F never changes. Once you've got that frequency, everything else, or the frequencies never change. Once you got it, never have to worry about it again. So F prime is equal to 5 times 10 to the 14 hertz. Now N is C over V. We've done that earlier. V is C over N, which is 3 times 10 to the 8th divided by 1.33, and that gives me whatever I had over here, 2.26. Which leaves only the new wavelength. When you're passing from one material to another, the index of refraction changes, the velocity of the wave changes, the wavelength of the wave changes, but never, ever, ever the frequency. Now you could do this one of two different ways. I've got the new velocity, so the new velocity is lambda prime F prime, which is the new frequency, which means that lambda prime is V prime divided by F prime. So this is 2.28 times 10 to the 8th divided by 5 times 10 to the 14. And that gives me a wavelength of 4.56 times 10 to the negative 7 meters, or 456 nanometers. And so that's a simple example of how light changes from one to another. And there is a whole problem. Well, actually, it's not a problem. It's a set of problems. Let's see. Page 4, number 8, rapid fire problems. What I've just explained, you should be able to do all of these now. So, I'm a lot like that. Whenever I see this, I think of that scene in Rodney Dangerfield's movie Back to School where the English professor says, I only have one question, but I have 75 parts to that one question. So that's how my problems roll. So Dr. Eschenberg, you've just been having fun drawing pictures, and now we've been doing physics for the last 20 minutes. I want to see some pretty pictures. Well, that's where refraction comes in. It was very interesting in, as an example, one of my former students who was a cheerleader, was working with the team, and they had, this was a field, and she was here, and her car was here. Horrible car, deal with it. This is a parking lot. This is a field of thick grass. So the velocity in grass is less than the velocity on the parking lot. You can move faster on asphalt than you can in grass. And she was here and she looked at there, and obviously the thing that she wanted to do was get to her car in the quickest amount of time. And a lot of people would just take a straight line because that's the shortest distance between two paths. She took the course. I was so proud of her when she told me this. And she realized this is a physics problem. And what she did was, she didn't head straight to the car. She kind of leaned her direction towards the interface of the grass in the parking lot, and then she banked towards the car. This path minimizes the time. And some call it the principle of least time. Other people call it the principle of least action. And action is actually action. You go, well, that's just distance, because all you do is you take velocity times the time and you minimize that function. But it's not a straight line. It actually minimizes the time. And another example, this is the example that I typically use. I'm going to take this off the sheet because I got to do the whole thing because it has a whole problem. You're a lifeguard. And your little lifeguard hut is over here. And initially placed out here, I put, so this is ocean. This is sand. And the velocity of sand is greater than the velocity of you in the ocean. And originally I put out there a drowning Justin Bieber. And I said, what is the optimal path to get to Justin Bieber? And the response of the class, I did not make this up, is, we hate Justin Bieber. I'm going to let that dude drown. And I'm like, okay, fair enough. So what I did is I said, all right, and immediately I changed it. Let me do something that will motivate you to get out there in the least amount of time. I said, you've got a box of puppies and the box is sinking in the ocean. Go save the puppies. And they're like, what sick person are you? And I'm like, well, someone who wants you to learn. So there's a box of puppies out there. What's the shortest path? Now there's some paths that are just downright crazy. You could go in this direction, go into the beach or go into the ocean, and then bank left once you're parallel with the puppies, but that's going to take forever. Or you could take this path and head towards the puppies, because effectively what you've done is you've minimized the length or time that you have to spend in the ocean, and you can move the fastest on land. But that's not quite right. You've got the path of least direction, the straight path, but you've got a lot of time on land, or you got a little less time on land and a lot more time in the ocean, and you're slower in the ocean. So the optimal path is something that looks more like this. Where you have to bank in a particular direction in order to minimize the time that it takes. You're going to spend a little more length on the land, but you can travel faster on land and a little less time in the ocean because you travel slower in the ocean. And there is a relationship that we have in this situation. There is this angle and that angle. That will be theta I, and that will be theta R. And what we've shown here is, actually I'm going to write it on a sheet of paper. So we got this. So what this is an equation called Snell's law, or law of refraction. That N1 sine theta 1 is equal to N2 sine theta 2. Oh, I'm already mixing it up. The way that it's written here, I would use NR sine theta R is equal to NI sine theta I, where I is the incident light, R is the refracted light. Here it's just whatever material 1, whatever material 2 is. If the light is set up like this, and you've got, that's the medium or the interface between the two surfaces, that's the normal line. You have theta 1, and you can have theta 2. And this is N2 and N1, that the angles will behave with relationship to the indexes or the indices of refraction. And that is the law of refraction, and that is Snell's law. How does this relate to the lab that you're doing this afternoon? Great question. And that is, from above, you have a crystal, actually it's not crystal, it is clear plastic, and it is a square. Now, once again, it's resting on a cork board, and when I'm talking about you're looking into the square, you're putting your eye literally where my finger is and gazing into it. And you put over here 2 pins, and what happens is that you're going to, I forget, what ends up happening is that you look in this particular direction and you will place 2 pins here. And those 2 pins, even though you see that the top of the pins are further to the right, above the mirror, below the mirror, you see the pins within the glass. And so these pins line up with the image of these pins within the glass. Now, hopefully I did it right. Probably not to scale. It's a little bit of a shift. Okay, there's just a touch of shift. And in fact, what I'm going to do is I'm going to draw it again, and now that I know what I'm looking for, I'm going to draw it better this time. The goal of this whole thing is find in of that plastic. And what I'm going to kind of do is I'm going to draw it out a little bit such that I know that I'm going to get something that looks a little bit more realistic. And what you'll find out is that this line is parallel to that line. So you look in this glass and you've placed 2 pins over here. Within the glass, you see those little green pins within the glass, and you put 2 red pins in there to line up with the image of those 2 pins within the glass. When you look at it, you'll see what I'm talking about. And what you'll find out, this is in glass, this is in air, this is in air. That should have been dotted. This is theta A. This is theta glass. This is theta glass. And then this is theta A. And what you'll find out is that those angles of theta A and theta G are identical. Those angles of green theta G and red theta G are the same within reason, because you guys are horrible, and including myself. I mean, we're not going to be precise. And green and red theta A's are the same as well. So you're going to have 2 of these sets of angles. You can use either one, and what's going to happen is that, let's say that theta A is equal to 45 degrees and theta G is equal to 30 degrees. So NA sine theta A is equal to NG sine theta G, which means that NA sine theta A over sine theta G is equal to N of glass. And this is what the last part of the lab is all about. But what do we know about the index of refraction of air? It's 1. So the N of glass is simply sine theta A sine theta G. Which means this is sine 45 divided by sine of 30. And I get 1.41. And so that's the index, that's how you get the index of refraction for a material, is you measure the angles that these things put out. And so I'm just taking a ballpark stab at the angles, but the answer that you get, I think you use acrylic, and it's in the 1.4, 1.5 range. Yes?
Where did NA, whatever you plugged in?
What is NA? And I said it 2 minutes ago. What is the A in N sub A? Air. N sub A is the index of refraction of air. What is the index of refraction of air? 1. So there's a little individual 1 in there that I just ignore. I mean, I don't ignore it, but 1 times anything is anything. And so that is the that. So index of refraction is kind of interesting, and there are real world applications. And one of the best things that I like are about critical angles and refraction. When so I live, the perfect example that I use, I live in University Trails, and my apartment is the best apartment in the whole complex. That's why I got it. I stood at the pool, I looked up and I said, I want that one. They said, you can't have it, it's taken. I said, I'll wait. And I waited a year, I signed the lease, and I moved in, and I haven't left since, because it's epic. I don't pay that much for a first floor facing the parking lot. 3rd floor looking over my domain is where it is. So how does this relate to refraction? Well, looking down at the pool, when it's full, you see what's at the bottom of the pool, which is in the bottom of the pool, they have the letters Ole Miss in tile at the bottom. So from my vantage point, I look at the pool and I can see at the bottom, well, they've been chlorinating the pool, so it's kind of milky at the moment. But when it's clear, you can clearly see Ole Miss written at the bottom. From time to time, they drain the pool. And all I see is a little bit of the lettering, the very top of the lettering. And so what happens is that in a situation where it's empty, I'm up here looking down at the pool. The lettering is down here, and it's blocked. So in black is the light of straight path. But if they fill this thing with water, what happens is the light refracts and it bends around the edge. So now I'm able to see it. So for a full pool, it was weird because I'm sitting there on the porch and I'm looking down at the pool and I'm like, where's this Ole Miss? Where did it go? Did they just pave it over or do whatever? They take it out? No, it was there. It was just because of refraction you couldn't see it. There are another interesting example is native tribes of Brazil and Eskimos. They discover that they're aware of physics, they just don't really, they haven't really quantized it or described it. But if you have a fish, let's say we're not gonna put bait on a hook and catch the fish of fury, we're just gonna stab that guy. What happens is that the light bends like this. So water going, or light coming from a substance where the index of refraction is bigger than that of what it's entering, the angle will get wider. So that's the angle of refraction. That's the angle of incidence. When n of incident is greater than n of refraction, theta I will be less than theta R. So spear fishers, or fishermen, aim below the image. So from your vantage point, it looks like the fish is here. But that's just the image of the fish. That's not where the fish really is. If you notice, take a stick, poke it in the water. What do you know about the image? It looks like the stick is bent. And it warps. It doesn't physically change the stick itself. It's just changing the image of it, how the light in your eye perceives what happened to your stick. So for this, the fish is truly in a different location where it appears to be. Another thing that you tend to notice is when you look down in a pool, you can see the object that's in the pool. But when you look down at the pool, then you start lifting your eyes up so that the angle when it hits the water is a steeper and steeper angle. Eventually you can't see what's underneath the water at a certain distance away. And what happens is if you have an object here so this is water and this is air. This is refraction. This is theta I, this is theta R. And then we deal with Snell's law in incident sine theta I is equal to nr sine theta R. At a much steeper angle, angles like this. If the object was here, the light would reflect off the surface. And you can definitely see it when you're underneath the water. Go underwater in the pool in Turner Center. Go about 8 feet down, look up. You could see out of the water. You can see the ceiling and all that stuff. But start looking towards the edge, further and further away from you, down the surface of the water. And what you will see is that the water surface becomes a mirror. It looks like a mirror. And what is happening is that at a particular angle, we've shifted from refraction to reflection. That the light no longer passes through, it simply bounces due to the laws of physics. In this particular case, that theta I is less than theta C, and in this case, theta I is greater than theta C. And theta C is the critical angle. The critical angle is when light when it hits the water, or when it hits the interface, the ray moves parallel to the surface of the water. In this particular case, theta I is some angle between 0 and 90 degrees, but theta R is equal to 90. So using Snell's law, N1 or Ni sine theta I is equal to Nr sine theta R. Sine theta R is sine of 90, or 1. Sine theta I is Nr over Ni, or theta I is equal to inverse sine Nr over Ni. So in the case of water and air, where water is the incident material and air is the refractive material, this just becomes sine theta 1 over 1.33. And we get we'll just say 49 degrees. I've rounded it. So you can get, if the incident, if this is at 49 degrees, the light will travel parallel to the surface of the water. If the angle is less than the critical angle, it will refract according to Snell's law. If the angle is greater than 49 degrees, it'll reflect. That is the angle at which we have a very special case at which the light comes up to the surface and then travels parallel to the surface. It bends a full 90 degrees, or 2 full 90 degrees from the axis. This is also, they call this total internal reflection. Okay. So that's total internal reflection. Can light totally internally reflect for light from air into water, i.e., what is that critical angle? So light can shine down into it, and then, but is there ever a situation where light can do its internal reflection thing? Well, what we've seen here is that sine of theta I is nr over ni. That this theta I is simply, and its sine is the ratio of the refractive medium divided by the incident index. So theta I, the incident angle where this can work, is inverse sine of the refractive medium divided by the incident medium. The incident medium in this particular case is air. Light is heading towards water, it hits it, what is its critical angle? So all we have to do is take the inverse sine of 1.33 divided by 1. What's the problem with this? What happens to your calculator when you try to take the inverse sine of 1.33? Domain error. It explodes. Your calculator just hiccups. This is mathematically impossible. There will not be a critical angle. So you can do a critical angle, light coming from water into air. It can do that. But if you're going from air to if you're going from a lower to higher index of refraction, you cannot have total internal reflection. If you go from higher to lower, yes, entirely mathematically possible. But Snell's law has an issue with that. And so all of this has been about refraction and reflection. And what we're going to do for the last 20 minutes or so is we're going to start talking about thin lenses and mirrors. So we're all familiar with a mirror. This is a plane mirror where if you had parallel light hitting a plane mirror, the light simply reflects back in the same direction. So for a plane mirror, it just does this. There is something called a concave mirror and something called a convex mirror. A concave mirror looks like this. So it bows outward. For a convex mirror, it bows inward. Now with the parallel light that heads straight at a mirror that's concave will reflect back. But light that's parallel like this will reflect like that, and then parallel light on the lower part. Oop, that's blue again. Where's my green? Parallel light will reflect like that. And what we see here is that there is a point where all three rays cross. And that is the focal point. And what you see here is that the light rays converge to one specific point. And we call concave mirrors converging mirrors. For a convex mirror, light rays that head straight at the lens reflect back. For rays that are parallel hitting the mirror, what ends up happening is that they reflect away. And these are called diverging mirrors. So a concave mirror is bowed, well, it's bowed outward. The parallel light rays that are initially all side by side will cross at a particular point, and that point is called the focal point. For a concave mirror, the light rays bend away, and it's a diverging mirror. But if you take the rays from the reflection and you trace back, they too converge at a point, and that is called the focal point as well. So both converging and diverging mirrors have points where either the rays focus on or the tracebacks of the rays, of the outward rays, focus on. So both of them do. And we label these focal points by the letter F. So F is the focal point F prime is the point opposite of F and has the same distance. So if the F is over here, the F prime is over there. If the F is over to the right, the F prime is over there. It is F prime is occasionally useful in ray drawings. That's an A. That's a horrible A. That's an A that has been drinking paint thinner, I guess. Ray drawing exercise, ray drawings, that's enough. So it's occasionally useful to do that. Now, the way that I typically draw the ray diagrams is I draw it. There is one horizontal line, and I call that the optical axis. There is a vertical line, and I call this the mirror or lens plane. I don't draw the lens or the mirror when I'm doing drawing diagrams. Everybody wants to be artistic with drawing the mirror and the lens, and they're drawing it so wonderfully, and they're trying to get all the rays to line up correctly. We just do not have the artistic expertise to draw it correctly. So what I do is I just draw a line, and I just say my mirror or lens is along that line, and it just follows what goes on. This is for a concave mirror. This is for a convex mirror. And the way that we do, right now all I'm doing is just setting these things up and how I draw it, and I'm going to do all the labeling stuff. Oh, I hate it when that does that. Okay. The mirror for both of these are along that line. This is a concave mirror, that's a convex mirror. A concave mirror has its focal point to the left. A convex mirror has its focal point to the right. If the focal point is to the left, its F prime is over here. If its F is over here, its F prime is over there. In 214, in all of the experiments that we have set up, in all of the problem sets that we have, in all of the problem sets, lectures, tests, all that stuff, the object, and it won't mean anything at the moment, the initial object is always on the left, and O is greater than 0. And in this particular case, I write the 0 with a circle bar, which is null, big deal. Objects will never be to the right of the mirror. There's no point. It wouldn't reflect. Why? Because it's on the back of the mirror. So the objects are always to the left of the mirror. Their values, or if the object is here, then that is the object distance. The focal point has its distance F there and its distance F there. If F for a mirror is to the left of the mirror, its value F is greater than 0. Concave mirrors have focal length values that are greater than 0. If the convex mirror has its focal point, it's to the right side, that focal length distance is less than 0. So if I said you have a mirror, what kind of mirror? I don't know, but I know that its focal length is positive 3 centimeters. You know that you're dealing with a concave mirror. Why? Because its focal length is greater than 0. If I said you had a mirror with a negative 18 centimeter focal length, you immediately turn and say, well, I've got a convex mirror. I've got a diverging mirror. So a lot of this is being able to interpret things correctly from just a simple number that's given to you. So how do we find our images created by the mirror and lens? In the test, for 214 test 3, what I'm going to do is I'm going to give you a mirror or a lens, and I'm going to ask you to describe the image that's created and then draw a ray diagram. So for something like this, what we're about to learn is critical. How do we find this? We use two equations. 1 over f is equal to 1 over I plus 1 over O. And that m is equal to negative I over O. Now, a lot of people, they use d sub f, d sub I, d sub O, because a lot of people get confused between that and a 0. I'm a human being, I'm a scientist, just as my teachers have taught me, I should be able to understand that in an optic situation, when you've got this just sitting there, that's not a 0, that's an O. Live with it. You can handle it. It'll be fine. But if you want to write df, di, and do, that is fine. That's no big deal. But I'm going to draw it like this. What you do is you solve for I to know where the image is. So solving for I, 1 over f minus 1 over O is equal to 1 over I, or I is equal to 1 over f minus 1 over O inverted. So just rearrange that. There are two possibilities. In the event that I is greater than 0, that it's positive, you know that the image is real. That you can put a sheet of paper and get an image at that particular location. If the I is less than 0, the image is virtual. So for a real image, the light rays pass through a specific region. For a mirror, the real region for both are on the left. And for the right region for both, it's virtual. So if you have a positive value for that image, the image will be over here. If you have an image distance that is negative, the image will be over here. If the image distance is positive, it is to the left and it is real. If the image distance is less than 0, it is to the right and virtual. This lets you know that you've got an image distance that is, if it's positive 5 for a mirror, it's to the left. If it's negative 5, it's to the right. This M is a magnification. It's a ratio of the image distance over the object distance, and you got a negative sign in there. If the absolute value of M is greater than 1, it's magnified. So something like that either becomes this or that. If the magnification number magnitude is less than 1, it has been reduced. And what we're doing now is we're just describing the image. The magnification is less than 1 or reduced. So something like this can either become this or that. If M is greater than 0, it is upright. So it could do something like that to this, or that to something smaller. One of the two. If the M is less than 0, it has been inverted. And all these arrows are just sample images. It's inverted. So a sample image like that can become this, or no, I take that back. It becomes that, or it becomes that. It has to get flipped over. So if I said M is equal to -2, it is inverted and magnified. So something like this becomes like that. So just from the magnification number and the image distance, you can figure out where this thing is and what it looks like. Now, we haven't dealt with any numbers, but the common distance that we'll be using, and it's the reason why we use this is because when you do the lab, we typically measure in this unit, are centimeters. There is another unit that we'll be using, and will be done in 1 minute, is a diopter. And they just use D for it. And we'll go more in detail about this tomorrow. And then a diopter, one diopter is equal to 1 inverse meter for its focal length. So if you had a +5 diopter mirror, its focal length is positive. There's a big positive symbol out front. So you're dealing with a concave mirror. Its focal length is 1/5 of a meter. You just invert that 5. And then you convert it, not to meters, to centimeters. And so a diopter is an inverse meter, and you can get the focal length of all sorts of objects from that. When you go to an optometrist and they write a prescription, and you see the +2.25 and +2.5, that lets you know that you're dealing with a certain lens with a certain focal length, and those 2.25 and 2.5s are all in diopters. That's the units that optometrists use. All right, that's it. Have fun in lab. See you tomorrow.